Great. Well, let's give Chris a round of applause.
I just wanted to say that Tom Sark is going to be talking in the next session.
All right, good morning, everybody. Today I will be talking about hydro control via slurry walls and CCR side. Before I start, how many people heard about slurry walls before? Good. For the people that don't know what's a slurry wall, that's what we'll cover today. Basically, it's going to be a slurry wall 101. We're going to keep it very basic. If you want more information, we have a booth for exhibitors. I will be happy to talk for hours about slurry walls. That's what I've been doing for roughly the last 10 years. It's a very specialized technique, and that's really a contractor's side of the operation. So that's what we'll cover today. The agenda here, we'll start with an introduction. I will explain all the technology, the equipment that we use, the three main techniques. There are more than this, but we'll just cover the three main ones. One very important topic, the key verification, one case study for a CCR site, and then after that we'll finish with a summary. So, as I said, I've been in business for about 10 years. I've been working for the same company, Forgen, for the last 10 years. Forgen, we're a geotechnical, civil, heavy construction contractor. We're a major player in the industry, either geotechnical, civil, or foundation. We can cover everything. We're doing projects that goes from 3 million to 500 million. We take all of them. When that's a good project, good client, we have no hesitation to projects, and especially for the slurry walls, we install over 150 million square feet of slurry walls. So that's really our bread and butter, slurry walls, and that's what we're pushing to do, especially for CCR sites, which currently is an issue that's coming, and that's what we're going to talk about right here. So currently in the U.S., there's 310 active landfills, 735 active surface environment, and 40% of them, well, they have groundwater that impact the groundwater quality standards, and that is an issue. And the EPA is still calling the legacy impoundment for landfills containing CCR. So here we have an issue that 40% of all those landfills, there need to be remediation to make sure that the environment is clean from all those landfills and legacy landfills. In 2015, the EPA here allowed the coal ash and all those landfills to be kept in place as long as there was engineering system to prevent the groundwater, any contaminant to go out of the properties. In Part B of the EPA in 2020, they allowed extensions. The facilities could not do it in time, so they allowed extensions, so people were pushing it. But then what happened last year is that the EPA denied extensions. So at this point, the facilities, they need to do something right away. They can't wait anymore. So that's what we're going to talk about today. One of the solutions that is acceptable by the EPA, we've been doing that for many, many years to prevent the contaminants to go outside of the CCR site. Basically, what the EPA said is, I'm not going to read all this. You can't just slap a cover on top of a CCR site and let the groundwater be contaminated and then go up. That doesn't make any sense. You cannot just cover the top. You need to make sure that what's in the ground also is contained. And to contain this, that's where we come, that you can install a slurry wall. There's other techniques that could work, but then sometimes there's some sort. There's going to be some time that you're still going to have some contaminant that goes out, and that's not something that a client wants. Take a risk that after that is just going to become a problem that's going to be occurring. So what you want is a solution that has no exposure, therefore there's no risk. And for this, a proven solution is the slurry wall. The slurry wall has been there for many, many years. We'll go through that later, but. So what is slurry wall roughly? A slurry wall, if I want to explain it in simple terms, it's basically a wall that you put in the ground that normally you're going to go key into a confined layer such as clay bedrock, or any low permeability layer to prevent contaminants or for our application, groundwater, if you want to keep it in or out, around the unit. So what that's going to do is everything inside the wall will stay here and the groundwater will go around it. Therefore, for landfills and any site that has contaminant, you contain everything inside and you don't let the groundwater touch it. As I said, the slurry wall is not new. There's some people that haven't heard about it, but it's been since the 1950s. Those are real pictures from the start of our companies. One is in Pakistan on top here, and here you see drag lines. We don't use drag lines anymore, not in our industry. We have better techniques right now, but it's been there for a long, long time, and technology has been better. At the beginning, there was some maybe flaws in certain project and everything, but now it's been proven with sites that has a lot of monitoring that once you install a slurry wall, you're going to be good with your contaminants. We've been installing slurry walls in CCR sites since the 1990s, starting in Pennsylvania, and we did many sites all the way to 2022. We did our sites for confidential clients that I cannot name, but we're doing it in many locations. Like I explained earlier, there's three main techniques for the cuff wall. There's a salt bentonite cuff wall, salt cement bentonite cuff wall, and cement bentonite cuff wall. Each of these techniques has pros and cons, and we'll go over that in the next slides a little bit. But before we go into the exact technique, we'll talk a little bit about the equipment we have. When I was saying that we're a major company and we have a lot of equipment, a lot of this equipment is this. Not any company has this. As you see there, that's what we call a long reach excavator. That's a normal excavator, but the rest is not discernible. It's custom made. So those excavators can go all the way to 90 feet deep. It's normally a conventional excavator. I mean, you have a big excavator that will go 20, 30, but with the long boom and long stick, we can dig all the way to 90 feet deep. And without big sport excavation that we'll explain later, sport excavation is literally our technique. So that's to 90 feet deep, but we're not limited to 90 feet deep. We can go 150, 200 feet deep. I said you just need to go key in that low permeability layer. So that low permeability layer is 200 feet deep, well, you need to go key in that layer. If not, you're going to have contaminant that will go under the wall and go out, and that will defeat the purpose of the slurry wall. So when you arrive at projects that are more than 90 feet deep, what we use is what we call a clamshell here. You see in the back there's a long reach excavator that can go to 90 feet deep, but then after that we deepen the wall with clamshells. So clamshells are attached to a crane, heavy duty crane, and basically what it does is just open, go down, close, you go back up, dump your spoil, and go back, and you go as deep as you want. This project here went 160 feet deep. In Canada in 2015, we went 179 feet deep. But like I said, there's not really a limitation. The only limitation you have is the amount of cable you have on the crane, but we can add cable. I mean, there's certain limitation at one point how much cable you can put on the crane, but projects 200, 250 feet deep, we could do it. It just, at one point, needs to be calculation if it's economically feasible or not, but we can do it. The three main techniques of the slurry wall, we'll start with the first one that normally is the most economical one. That's the one that is most used in the United States, and it's a salt bentonite cutoff wall. So a cutoff wall, like I said, we go at depth, 90 feet deep, but we don't use shorings, we don't use anything like this because our sport of excavation, like we see here, is a slurry. Slurry is water mixed with powder bentonite. So the slurry will create a pressure on the outside of the trench walls that will keep the trench open. There's some calculation about stability analysis for a certain site with soft soils and everything. We're not going to go into those details. We'll just keep it to a good side that the slurry will support it. So the long reach excavator that you see to the left will excavate under slurry. So the operator doesn't see the bottom. He just dig into liquid to make sure that the trench stays open. We mentioned many times it's keyed into an aquifer. low permeability layer. I will repeat that because that is very important for slurry walls, and there I will have exactly a slide on this for key verification. And once the slurry is in the trench, well, you cannot leave the slurry in the trench. It's not a low permeability material. So you will go displace the slurry with backfill. We'll call it solventinide backfill. The solventinide backfill, why this technique is economical, is normally you will reuse the spoil of the side. Your exterior will deposit the salt to the side, and the salt will be blended with slurry and will be pushed back into the trench by a dozer or an excavator, creating a low permeability cutoff wall. When I say low permeability, see here normally 110 minus 7 centimeters per second, so there's barely no flow. And these type of flow are acceptable by agencies such as EPA for containing contaminants. It is low enough that it is good. It is technique that's acceptable. One cons of this technique is that there's no strength. Since there's no cement or knotting, no region, there's no strength. So if it's done to support a landfill or something to the side, well, you need to do some calculation if you need some strength, because after that, if you have a landslide failure or something, well, you're back to where you were before the slurry wall. I explain a little bit. Here it is all the trench will look like at the beginning. Like I said, once you excavate with the slurry, you need to displace the slurry, but you can't just dump a slurry solventinide backfill in the trench. It's like when you do a trimming pipe. You cannot just dump everything and just hope that it's going to be fine. There's going to be pockets of air. So to prevent this, what we do is we do a laden trench to the left, and we push the backfill, which looks like concrete, has a slump of about 6. So with the dozer just pushing it, the backfill will slide all the way to the bottom, displacing the slurry and preventing some pocket of air. The slope will not be a 1-to-1 or 2-to-1 that we do a lading slope. Typically, it will be a 10-to-1 slope, which means if you go to 150 feet deep, yes, you will have a 1,500 feet long trench open, which is not an issue. It's fine. There's calculation that shows that the trench will be supported, but it's pretty impressive to see when you have such a trench open. And once the backfill will reach its natural engulfable growth, that I talked about roughly a 10-to-1, on top, it will start to move, and that's what you're going to do for the whole length of the cutoff wall. The exterior will dig, you're going to backfill, you're going to fall like this, and at the end you close your trench, and your cutoff wall is installed. Very simple technique, but proven technique that is being installed on many sites. The second technique, salt cement bentonite cutoff wall. Very, very similar to salt bentonite. The major difference is that you add cement to your backfill. When I say that the salt bentonite cutoff wall didn't have no strength, well, you can remedy that by putting some cement into the backfill. You're going to batch a little bit like the left here. You're not just going to mix it with a dozer like the salt bentonite. You will need to have your proportions right, because you can't just dump cement and don't know exactly the proportion of your backfill, because there's a backfill mix design and everything to make sure that you meet the contract requirements. One cons when you have the cement is that here, the permeability, or the average conductivity, is 110 to minus 6 versus the 110 to the minus 7 of the salt bentonite backfill, because the cement will actually increase the average conductivity, but will be able to give you some strength. So if you need strength, you will need to sacrifice a little bit the hydraulic conductivity, but with the engineer's calculation, normally the design can account for this. You can have other methods in place to be able to meet still the design intent. The third technique, it is quite different from the two first techniques. The two first techniques, you excavate under slurry, and then after that you display the slurry. For the third technique, the support of excavation is the backfill at the end. Now at the beginning it's liquid. You cannot excavate under something that's hard. So you excavate under liquid, but compared to the other technique, which was wire and bentonite, this one will be cement, wire, and bentonite. So the excavator will do as usual, will excavate. There's not going to be any backfill mixed by the side. The support of excavation will be mixed in one of the CV blend that we have here, cement bentonite plant, that is all own equipment that batch the backfill to ensure that you have the exact ratios to meet the contract requirements. As you finish your trench, you will leave the liquid there, and the liquid is going to harden into the trench, and will give a very low permeability material of 110⁻⁷. 110⁻⁷ can be even lower. We can go 510⁻⁸, but typically it's 110⁻⁷, and you can have strength. And another advantage to this technique is that there's some sites that you cannot reuse the material. You're trying to sometimes go to contaminated material. If you have contaminated material, sometimes you don't want to reuse it, place it next to the trench, push it back in it. Sometimes it just don't make sense. So you will leave it there, and it's going to be a final backfill. It's going to look a little bit like the bottom left pictures. It will turn green. It's just because of the slag cement normally that we put. There's no color in nothing. It is the final backfill. You leave it there, and it's this. For sides that have very soft material or very high groundwater, cement bentonite sometimes is the best technique, because I explained the salt bentonite that you have a 10-to-1 slope and sometimes at 1,500 feet long open. If you have soft soil, well, trench stability can be an issue. The cement bentonite technique, you will open what you do during a day, which could be 100 feet long, but then after that it's going to harden, so you're going to have less issues with trench stability. Topic that I mentioned before, the key verification. There's different techniques for what we call cutoff wall. Cutoff wall can have deep soil mixing, can have jet grout, can have other techniques that some people know, some people don't. But one big advantage of the key verification in the slurry wall world is that you can actually see it. There was a study from the EPA that studied many sites. Studies from 1998, but still valid to this day, that the biggest issues with the slurry wall that was installed is that they were not properly keyed into the aquifer. So when I said that you need to go reach clay or reach a low permeability material, if you don't do it, because of the gradient across the wall, all the pressure, well, you can have a low window and it will be 95% of your flow. So if you cannot confirm by borings before the fact, or during construction, that you're well keyed into that layer, it's not going to work. It is one of the most important thing about slurry walls. If you have the best backfill in the wall, but you have a window, it's not going to work. The advantage of the slurry wall, like I said, is that you can see the material, because we excavate under liquid, and you can deposit the spoil to the side. The engineer can go see the material. You can go touch it, you can run testing if you want. And if there's a variation in the ground, you're going to see it right away. There's some techniques that will mix the ground in place, and if you don't have enough boring, well, if there's a dip into the clay layer for whatever reason, it can be a river that was there millions of years ago, or any other reason, well, you're never going to see it. Here, it is a project that we did in Saskatchewan, Canada, that it went roughly 5 meters deeper, or 20 feet, 15, 20 feet deeper, like this. And we weren't sure why, but at this time we had clamshell and we could verify it. Once the operator arrived at the depth on the plans, we're like, there's no clay. We cannot just finish that. So we deepened the wall automatically, and therefore we confirmed that the wall is going to work. And it is the most important thing, like I said, and the slurry wall will prevent all this. And that happened on many sites that contractors, after monitoring, had to go back because it wasn't keyed right. The key, most important thing about the slurry walls, the cutoff walls, or any method, if you go with any methods that prevent a flow, if it goes under, there's no point of doing a wall. So a little case study. I cannot say where the project was or who the client was for confidential reason. A lot of clients don't like to say that they remedied their site because it was contaminated. So we'll keep it very general, but it is a site that we did in 2022, and we have a third phase coming. We did 2 phases, and there's a third phase coming. That's an ash pond closure in place. The company contracted us to do roughly 5,000 feet of cutoff wall to a depth of 50 feet, and we helped with the design of the cutoff wall. First, the cutoff wall was as a soil cement bentonite cover. Like I explained, the soil cement bentonite cover wall has a limitation on the hydraulic conductivity. And when we started talking with the engineer and client, they were looking something that was less pervious. So what we worked with the engineer is to change the soil cement bentonite cover wall to a cement bentonite cover wall, and we said it can achieve some hydraulic conductivity lower than 110-7 centimeters per second. So that is the first thing that we did. Then we developed a mixed design that was able to have a UCS, unconfined compressor strain, 28 days between 30 psi and 200 psi. We can go all the way to 500, 600 psi, but sometimes you want less strain, a little bit more strain to be able to get some loads. And also what we did for that project, because the engineer was very curious about technique, that was first time was working with this, the client also is, we did a test section. Test section was short, but very expensive in testing. So we installed the test section, and after that, the engineer wanted to see is coring. So we cored the wall in multiple locations to confirm that we were well keyed into the chalk, which is the low permeability material that we're keying into. And also the cement bentonite gulf wall, like I explained, if you do one panel, it's going to harden, but then after you need to connect multiple panels, and you're going to do overlaps. The overlaps, sometimes there's people that will say that there's going to be a seam, and there may be some water that's going to flow because you excavate the liquid into a hard material. It is not true. And we verified it there. So we did, if I'm not mistaken, 4 borings to verify that the depth was right, was well keyed. We did 1 boring at an angle to verify the overlap, and you could never see the overlap. That is the picture of the overlap. Okay? There's 2 walls that were installed 2 different days, but you don't see it. And at the bottom, I will clarify that here the little crumble here is because of the low strain material of the cement bentonite cuff wall, which is maximum 200 psi. Once the drill rig arrived at the chalk, it turned around, and then after that, it kind of destroyed the wall, which is normal. But we have many studies that show that it doesn't look exactly like this, but because of the mechanical fracture by the boring machine, well, that's what it shows. But there's perfect contact, and so the engineer was satisfied. We uncovered the side of the wall also, and the engineer was satisfied. So we went ahead and installed 200,000 square feet of cement bentonite cuff wall. And once the project was done, there was some monitoring on site to ensure that the cuff wall was working. Normally in monitoring, you will have a piezometer on one side of the wall, piezometer on the other side. You will see a difference in the groundwater elevation, and you can sample also your groundwater to make sure that the contaminant doesn't go up. So after we install all the system, the contaminant was not going out. So the client was happy, and that's why we're doing multiple phases of the cuff wall. And it's going to continue on that side for many years. But it is not the only side where we did. Like I said, we did since the 1980s, but it's a very recent project. Here, some items that some engineers do like also is that on the exterior that we had a GPS monitoring system, so that has the exact location of the bucket in the ground. I mentioned that you excavate a liquid, you cannot see the bottom of the trench, so with the GPS system, you can draw on AutoCAD or whatever your exact profile from the GPS monitoring system. There's our technique, but that's the latest technology, and also for the overlap to ensure that you have a good overlap. And our CB mixing plant also is equipped with scales that calculate every batch. To ensure that your wall is going to work, you want to make sure that you have a backfill that is homogeneous everywhere, and you can sample one location, but what says that the other location is the same? Well, every single batch that we do into our mixing plant, the ingredient is weighted. We have weight scale everywhere. That way we can ensure that if we said that we're going to put 20% cement, we can confirm that we have 20% cement. And then after that, there's a report to do and send it to any agency, the APA. Well, you can show that everything was there, everything is per mix design, and everything will have low permeability and will meet the design intent. So, as a summary, slurry walls, like I explained, the real goal is create a wall around it to make sure contaminants stay in and the groundwater goes around. And that's very relevant to the issue that we have here with all the active CCR landfills and any other project. I mean, it's not just about CCR landfills. It's about it can be a company that pollutes the groundwater under it. There's many applications. There's applications also for levee system. We do a lot of levee system to prevent the groundwater to flow under embankments. Or in Colorado, what is very popular is they mine the water, they mine the gravel, and after that they resell the water, so they don't want to lose their water that goes out. So if you want to keep water in or out, a slurry wall most of the time is the most economical technique. I'm not going to say all the time because I will be a car salesman here. Sometimes there's a better technique, but most of the time a slurry wall will be the adequate technique for such project. And here I'm gonna mention it again because it's very important. I think the biggest advantage of the slurry wall is the confirmation of the key. I will sound like a broken record, but if you don't key into an appropriate layer, you're not gonna have a good product. And that goes with this. If you have an exposure or risk of exposure by a window along the wall or by any technique that you use, well, you're gonna have a risk. And when we talk about contaminant, you don't want no exposure, you don't want no risk. And that's why, in my opinion, the slurry wall is the best technique, it's proven technique. And if you want to have more details on any of those techniques, like I said, we have exhibitor booth down there. I will talk for hours about slurry wall, and we can do also presentation for any company. We like it. We do lunch and learns with many companies about one technique, multiple techniques, or different techniques that we do. I mean, I talk about sometimes a soil mix that is not the adequate technique, but in some projects it is, and we do that also. But here we talk was about slurry wall, but we do many techniques. So we do the foundation, we do plenty of stuff. So please don't hesitate to come see us at the exhibitor booth if you want more detail. If you like to set up a call or a presentation with your company, we're there to help. And we like also to do design assist. We do multiple design assists because it is a very specialized technique. And on the contractor side, we can identify if there's a flaw into design as far as the constructability. When you bring big equipment like this, often there's some details that are forgotten, like enough place for the crane or issue with the trench stability. We can recognize this before the documents are out. So that's all things that we can help you with. And this is it for the cutoff wall slurry wall 101. And thanks for listening. And any question? Oh.
No, go ahead. I already had mine.
The drop will be below 200 feet. That was said how to do that. If you have to go below 200 feet. First person, second person, might pass.
Yeah, well, 200 feet, you know, at one point, 200, I will say, I could comfortably say that we can go 300. After this, you will need to use our technologies. I will mention one, hydro mill, which is technology, I think. Now they're going to 1,000 pp, which, yeah, is very deep. But then at one point, the cost also is there. Those are huge machines. We don't own such machine. We don't do that technique. It's not our level. But really, when you go to huge depth like this, 1,000 feet, you will need to change technique because at one point it's going to be too deep. Because one issue with the, not issue, but one challenge with the slurry wall is that if you deviate at one point, if your excavation deviate by this much at an angle, well, if you go 1,000 feet, you're going to deviate, and maybe you can have a window at the bottom of your wall, which I said you don't want that. So you want to make sure you have the right measure in place to ensure that the overlap or any bottom of the wall is continuous. So that's why I said 300 feet is where what we'll be comfortable with, and then after that you change technique. It's getting deep at this point.
Very interesting.
Yep.
Have you had to deal with maybe blowouts where like the formation pressure is higher and you have maybe like the brick coming up the surface? Have you had to deal with something like that in the artesian?
Yeah, so yeah, we have to deal with artesian conditions in multiple places, and that's when really trench stability analysis is important. What you can do with trench stability with artesian conditions, you will rule of thumb, you will always try to ensure that your level, piezometric level, is going to be within 3 feet of your slurry level, which create the outside pressure of the walls. But the heavier your slurry is, or the higher the elevation of your slurry is, that's what will prevent those conditions to be unstable. So what we can do in a case of salt cement or salt bentonite or cement bentonite, you can actually add sand to the slurry that will create denser slurry, and then that's going to create more pressure. Sometimes what you will need to do to have a higher elevation for your slurry, you will need to raise the work depth. There's multiple techniques, and what I said about the cement bentonite cutoff wall, cement bentonite cutoff wall is done panel, and when you get a panel, what you get on the trench stability analysis wise, you will get the arching effect of the panel. On the salt bentonite with the trench open, you will analyze it as 2D analysis, infinite continuous range. But when you get into panels, you will get the arching effect that increases greatly the trench stability. But yeah, we went to weight of hammer material that you go through plenty of it. Sometimes there's some material that will be on top of rock, and then you try to get in the rock, so you will need to assume for the vibration, and there's a lot of calculations that goes into it, but typically there's always a method. I'm not going to say that it's always the cheapest. When you raise a work pad, a lot of times it can be expensive, but then you can balance in between raising the work pad, increasing your slurry density, or using maybe a panel that's smaller. So there's multiple things to do, but yes, it is something why you don't want to hire somebody that don't have all that experience, because trench collapse happen in many sites, and that's not something that you want for sure. But no, very interesting question, because yeah, it happens all. Yeah.
Just from a hydrogeologist standpoint, we view the slurry well as part of the groundwater extraction system. So from that standpoint, just sort of point out that we often want windows and not heat in those cases, because we're trying to manipulate the flow system, not necessarily create a complete barrier. And there's cases where, for example, if there's low permeability units and we can't get enough head to pump the groundwater, we want to raise that head. And the other is sustainability. We sometimes don't want we want to shut the pump system off and let the water flow through. So there are cases where that heating and window thing, I get it, it's important. But I just wanted, if you could just briefly address, be that car salesman and tell me, what are the advantages of slurry well over like sheet pile?
Cost.
Okay.
A lot of it's going to be cost.
Okay, so it's more expensive to drive a lot of pile.
Oh yeah.
Okay.
Yeah, it will. Yeah. Normally, I mean, I can't give a good number, but you go see slurry well that's half the price of a sheet pile, because the price of material mostly. Sheet pile, a lot of material, and price.
Yeah, we just see that so often that people will default to sheet pile, but I guess that's.
Sheet pile seems so simple, and it's been used, and I don't know. I think that's because
expensive is what you're telling me.
Yeah, and I think that's because a lot of people are not comfortable enough with slurry walls. That's all I'll say. And sometimes, I mean, because there's limitation also on work area that you have. I mean, if you just have 10 feet, we can bring big excavator or crane and everything. So there's some advantage to the sheet pile, no doubt. But normally, what throws off a sheet pile is the cost. Yeah.
So I'll ask one question. I've mentioned our Gophers program, which is all about underground power distribution. We should talk offline, but my direct question is, do you have any applications where you use your slurry wall system to essentially improve the resilience of an underground power distribution system, especially, say, at high-risk points?
I never did one myself.
Yeah.
I will need to verify with the
Sure.
guy that's been doing that for 40 years, that may have well done it. But yeah, we'll have a talk for sure, because it's been applied on many different applications. But yeah, I can't talk for that myself.
Sure.
Yep.
We have not, but I will say we've actually been approached by like companies like PG&E, where in California they have to underground a certain amount.
Sure.
So that has been something they've talked to us about, and it's something I think we're looking into. It's just some of them aren't going as low as we need it to, but yeah, it's something we're looking into.
They've been very active and very helpful with us on our Gophers program.
Okay.
So, terrific.
Yeah. That's a big thing in California with all the wildfires that happen. When some of these actions have happened, they've been mandated to underground a certain amount of their systems by a certain time, I think it's like 5 or 10 years or something like that, yeah. So they're really heavily involved in that.
All right, thanks, everybody.
Well, thank you. So it's great that we've had the extra time for the technical experts. I'm actually going to back us up a little bit higher and talk policy in the space here. So let me just get my slides up.